right, we're going to look at some more different types of voltaic cell problems that you might see. These problems are all from old AP exams, so you can see different variations. So we've got the standard kind of voltaic cell problem in which you're given the two half reactions and you're trying to figure out what the overall reaction is and what's the voltage. And from the voltage, you could find delta G. You could also use delta G equals negative RT ln K to find the equilibrium constant. So there's a relationship between voltage and equilibrium and delta G. So that's cool. We're seeing all those connections here. But there's different types of applications we might see. So let's take a look at some of them. So here's a problem where we are asked to consider a variety of voltaic cells we could make, and you want to identify the two metals that could be used to make an electrochemical cell with the largest voltage. So here's your list of three metals. So we've got three possibilities. We could put platinum with nickel, we could put nickel with silver, or we could put platinum with silver. And let's look at them individually. So platinum's we know the one with the highest reduction potential will be reduced. So in this case, platinum would be reduced, and that would be plus 0.12. And nickel has the smaller reduction potential, so nickel would be oxidized, so we would flip that around. And that would give us a voltage of positive 1.43 volts. Okay, now look at other possibles, nickel and silver. So if we look at those two, nickel and silver, it looks like silver would be reduced. It's got the higher reduction potential. Nickel would be oxidized. That would be positive 0.23. So that's going to be 1.03 volts. Not as high, so we're going to eliminate that one. Okay, and then platinum, silver. So in that case, platinum would be reduced because it's got the higher reduction potential when you're comparing. And now here we're comparing these two. Okay. Silver would be oxidized. So you would flip the sign around, and that would give you 0.4 volts. So it looks like the highest voltage right here is the platinum nickel cell. So you're just kind of comparing three scenarios, almost like three little problems at one. Okay, and explain how you arrived at your answer. You could, doing some mathematical work, like showing the three voltages would be one way of doing it. You could also explain something in words. There's a variety of ways in which you could explain this. And if you look at the second question, part B, predict whether platinum metal will react when it's placed in a solution of 1 molar silver nitrate. Justify your answer. Notice I put a hint underneath it. This hint would not be given to you on the AP test, okay? But this is what I want you to think of. So if it says predict whether something will react, and that's basically, it's asking you, is the process going to be thermodynamically favorable? So is it going to be spontaneous? That's what you want to think about when you see, like, will this thing happen? I mean, is it going to be favorable? And in order to figure out if something's thermodynamically favorable, you need to look at the sign of delta G. And you can find the sign of delta G in a variety of ways. We got three equations here, right? We can use H and S. We can use RT ln K if we know the equilibrium constant, or you can use negative NFE. So you want to ask yourself, what do I know? Well, they're not telling me anything about the enthalpy or entropy. I am not given the equilibrium constant, so I need to use this relationship right here. So to figure out the sign of G, I have to look at the sign of E. So if E is positive, then delta G is negative, based on the math here. And if E is negative, then delta G is positive. So I'm just really figuring out what is the sign of E here. And so then you have to ask yourself, well, what reaction would happen? So if you were to put solid, solid platinum, in a solution of silver ions, what you would get is you would have the oxidation of platinum and the reduction of silver. Okay, so the question is this reaction favorable? And you can figure this out by looking at the reduction potentials. So this reaction shows platinum being oxidized. So I'm going to take this reduction potential here and reverse it. So platinum being oxidized is negative 1.2 volts. This shows silver being reduced. That's positive 0.8 volts. If you add those up, you get negative 0.4 volts as your answer. So it looks like E is negative, so G would be positive. So you have a negative E, so you'd have a positive G, so this would be not spontaneous. So this one comes down to like reading the question carefully and thinking, what are they asking me? Really, they're asking me, is this reaction right here spontaneous? So what is the sign of G for that reaction? Okay, looking at this problem, notice how this problem is different from the first ones we did, because instead of being given two reduction potentials and being asked to find the overall reaction, you're given one of the potentials and the overall, and you're trying to figure out what the other reduction potential is. And usually we figure out who's being oxidized and who's being reduced by looking at the standard reduction potentials, but we're not given both standard reduction potentials, so we have to look at what we do know. And if you look at this reaction, it looks like in this context, copper is being oxidized, right? Because we can see solid copper is going to copper ions, and then it looks like your nitrate over here is on the reactant side, which kind of matches here. So it looks like your nitrate's being reduced. So what I like to do is I'm going to write these reactions out as they occur up here. So this reaction is, we're going to flip it, because we can see up here that in this reaction, overall reaction, solid copper is turning to copper ion. So we need to take this reaction and flip it around. Okay, so solid copper is turning into copper ions. Okay, so my voltage, my sign's going to flip, so it's going to be negative 0.34 volts. And then my other reaction is going to occur as written, so nitrate and 4 hydrogens and 3 electrons. Okay. And this one we don't know the voltage of, but we do know your overall reaction has a voltage of 0.62 volts. It looks like my copper is losing 2 electrons, my nitrate is gaining 3 electrons, so we would, in order to get the balanced reaction, we would have to multiply the top reaction by 3 and multiply the bottom reaction by 2. But remember, when we multiply these half reactions by a coefficient, the voltage does not change because the voltage is a ratio. So it doesn't affect this 0.34 number at all. Okay, so we know 0.34 plus something is 0.62. So this number ends up being 0.96 volts there. So our unknown, standard reduction potential is 0.96 volts. Okay, cool. If you look at this last one, this is another Voltaic cell where you're given the half reactions and asked to, figure out what the voltage is. So let's just draw this out to remind ourselves what's going on here in our Voltaic cell. So really what we have here is we have a solution on, we got a half cell on one side that's got solid manganese, and then down here in the solution you've got some manganese ions, and you've also got some negative ions down here. It's something, maybe they're nitrates, it's just something that allowed us to dissolve some manganese ions in water. And over here on this side you've got some solid chromium, and then you've got some chromium ions here, and then you've got some negative anions that are going to be in this solution as well. And so we connect them with a wire, and we have a salt bridge. Okay. And the salt bridge contains other ions, like often like sodium nitrate is a good thing that might be in a salt bridge. It's just gonna be some sort of salt, which just means an ionic compound. And they need to be mobile, so they might be like dissolved in water, and maybe there's like some sort of like porous filter on either end. Or in class we use a piece of filter paper, and the ions can actually travel along the filter paper. So you need a salt bridge to make this go. Okay, so your standard cell potential, you're going to look and say, okay, who is going to be reduced, who's going to be oxidized? It looks like my chromium is better at being reduced. Okay, it has the larger standard reduction potential. Okay, so it's got so let's write that one out. Boom. So over here, my chromium is being reduced. So my chromium ions are turning into solid chromium. So over here on the other side, this one is being oxidized. So my solid manganese is turning into manganese ion. So when you flip this reaction, you flip the sign. Okay. And thinking about vocabulary, we can say, oh, look, this is a reduction. So red cat, I can now call my chromium electrode the cathode. And over here, this is an oxidation, which I know because we're losing electrons. So anox, that means my manganese is the anode. All right. And I can find the cell potential by adding up my half reactions here. Um, when I add them up, I tend to like to write them just one right above the other. So I'm going to rewrite this one over here. Okay. And notice in order to add them up, I need to multiply this number by 2 and then multiply this one by 3. Because I need to have 6 electrons gained and 6 electrons lost. But remember, when I multiply the half reaction by a coefficient, it does not change my voltage. This is where it is unlike Hess's law. Um, has to do with the fact that the voltage is a ratio of joules per coulomb. So, okay. So if I add these two numbers up, I'm going to get a positive number, which is good because I'm told that it is a voltaic cell. And this whole worksheet's called voltaic cells. So for voltaic cells, I'm expect the cell potential to be positive. So the cell potential is going to be plus 0.45. We did the work over there. The Gibbs free energy, delta G equals negative NFE. So N is my moles electron. So it looks like in this reaction, there are 6 moles of electrons transferred for every 1 reaction unit. And Faraday's constant tells us that it's this many coulombs of charge per every 1 mole of electron. And then my volts, I can also think of as being a joule per coulomb. So 0.45 joules per coulomb. So if I cancel things out, my coulombs cancel, my moles electrons cancel, I am left with negative like 300,000 joules per mole reaction, which I want to write with 2 sig figs, which would be negative 3.0 times 10 to the 1, 2, 3, 4, 5, 10 to the 5th joules per mole reaction. Okay. Since I have a negative delta G, this is going to be a favorable reaction, which means I'm going to end up with more products than reactants at equilibrium. And so my K value would be greater than 1. Okay, if I wanted to find the value of K, I could use this equation, delta G equals negative RT ln K. I don't have to find the value, though, here. I just have to say, is it greater than or less than 1? And then going back over here, if we're looking at this, some other things to keep in mind with your voltaic cell is what's happening to the mass of the electrodes over time. I'm gonna use a different color pen for a minute. Okay, so over here at the cathode, your chromium electrode over here, as this reaction proceeds, you're going to be making solid chromium. So your mass of your chromium electrode is going to increase over time because you are making more chromium in this reaction. So basically the chromium ions are coming over here and they're sticking to the solid chromium. On the other side, you are using up manganese. It's turning into aqueous manganese. So basically it's like your solid manganese is dissolving. So your mass of your manganese electrode is going to decrease over time. And then what's happening in the salt bridge is over here, as you are making more manganese, as the reaction proceeds, you're going to start making more manganese. You are going to have a buildup of positive charge. And if you have a buildup of positive charge, then let's think about what our electrons are doing. Our electrons are going to want to be flowing from your oxidation to your reduction. So they'll want to flow this way. But if you build up positive charge over here, the electrons won't want to like move away from a positive charge. They're attracted to positive. So that's one way I think about it. Like, oh, why isn't that good? So if you have a buildup of charge, your electrons will stop flowing through your wire. And so that's what the purpose of the salt bridge is, to maintain the neutrality of your solution. And then we're talking about electric, neutrality. So this solution is becoming more positive. In order to neutralize that, some nitrate ions from your salt bridge are going to move over here to neutralize those extra manganese. On this side, my chromium ions are getting used up. Okay, so we're going to have a buildup of negative charge over here. So that means that my sodium ions from the salt bridge are going to move this way to maintain the neutrality of this solution over here. So that's the purpose of your salt bridge, is to maintain the electric neutrality of the solution. And it's these ions that move in the salt bridge, not electrons. So the electrons flow through the wire from the oxidation to the reduction, and then ions move in the salt bridge to wherever they are needed in order to maintain a neutral charge in the solution.